All right, let's talk about the absolute bleeding edge of computer chip design. We're getting into custom silicon and some incredible new ways engineers are finding to just smash through the old performance limits. So let's dive right in.
So for decades, right, the whole game was simple. You wanted a faster chip, you just made the parts smaller. That was Moore's law. But what do you do when that rule just stops working? I mean, this is the core problem, the big question mark hanging over the entire world of computing today. And this isn't some far-off academic problem. It's happening right now. You've got Mark Kumerly from Marvell basically saying, hey, that reliable doubling of performance we all took for granted, yeah, that's not happening anymore. The thing is, the big data centers, the AI models, they couldn't care less. They need more power, more performance every single year.
Okay, so if we can't just keep shrinking our way to a win, what's the next move? The answer, and this is the big pivot for the entire industry, is customization. We're shifting away from one-size-fits-all and instead getting really, really creative, designing these highly specialized chips that are tailor-made for specific jobs.
And you got to understand, this isn't some small niche trend. We're talking about a market for these custom devices that's projected to hit $55 billion by 2028. That's not an experiment. That's the whole future of high-performance computing right there.
So this brings us to what the industry is calling the performance wall. It's this idea that we've hit a point where the old ways of getting faster just aren't cutting it anymore. We need something totally new. And that brings us to our first big solution. It's a really brilliant shift in thinking. If you can't build smaller, well, you've got to build smarter. And in this case, building smarter means building upwards.
And this is where the chiplet comes into play. So instead of trying to make one single gigantic perfect piece of silicone, which is incredibly difficult, designers are now using these smaller, specialized modules. You can seriously think of them like super advanced Lego bricks. You stack them, you connect them, and you create something way more powerful and flexible than you ever could with a single block. And the difference here is just night and day. The old way, the monolithic chip, it has a hard physical limit. You literally can't make it any bigger than about 800 square millimeters. But this new multi-die approach, it just shatters that limit by going vertical. You can stack chiplets on top of each other, which means you can cram in an exponential number of transistors without needing any more space on the board.
And just look at the results. This kind of 2.5D packaging lets engineers cram 2.8 times more computing silicon into the exact same footprint. That's not an incremental improvement. That is a massive, massive leap in density and raw power. You know, this quote really says it all. For years, the packaging, the thing that holds the chip, was kind of an afterthought. Nobody really thought about it. But now, it has become a key differentiator. It's just as important as the silicon itself, maybe even more so, when it comes to pushing performance. Okay, let's switch gears to our second solution, because this one tackles another huge bottleneck: memory. You can have the most powerful processor in the world, but if it's just sitting there, starved for data, it's totally useless. So we need faster, way more efficient ways for that processor to get the information it needs. And that's where SRAM comes in. SRAM stands for Static Random Access Memory, and it's the absolute fastest memory you can get. Why? Because it literally lives right there on the chip die, sitting right next to the processor. It's like the processor's personal super-fast notepad for whatever data it needs, like right this second.
But of course, there's always a trade-off, right? So we have this whole memory hierarchy. You've got SRAM on the die, it's the smallest, but it's the fastest by a long shot. Then you move a little further out to HBM in the package, and you get more capacity. We're talking gigabytes, but it's a bit slower. Go even further out to CXL on a different board, and you've got terabytes of space, but it's slower still. And that's exactly why optimizing that tiny, ultra-fast slice of SRAM is so incredibly critical.
And here's the payoff. By designing custom SRAM, engineers can pull off something amazing. They can actually reclaim up to 15% of a chip's total area. Think about that. That's a huge chunk of real estate you can now use for more compute cores or other new features, all without making the chip any bigger.
And the wins just keep on coming. It's not just about space. This custom SRAM uses up to 66% less power when it's just sitting there in standby mode. I mean, that's a massive efficiency gain. At the end of the day, that means a chip that runs cooler, uses less energy, and can ultimately perform better.
All right, let's get to our third and final innovation. So you can think of a modern chip as a tiny, bustling city. And just like any city, it needs a really robust power grid. The problem is, as these chips get more and more powerful, just getting clean, stable electricity to them becomes a massive, massive challenge. This problem is being solved with a pretty cool technology called PVIR, which stands for Package Integrated Voltage Regulation. Now, the best way to picture this is to go back to our city analogy. Imagine the city's main power plant is located 50 miles away. You're going to lose a lot of energy just getting the power to the city, right? Well, PVIR is like picking up that power plant and dropping it right inside the city limits. It just makes everything dramatically more efficient.
So here's the big idea. The old way, you had these voltage regulators sitting inches away on the circuit board. That electricity had to travel a long, pretty wasteful path to get to the chip. But with the new PIVR method, those regulators are integrated directly into the chip's own package. You've created this super short, super efficient highway for power delivery.
And the impact of this is, well, it's a total game changer. By shortening that delivery path, you can cut the amount of power that's just lost during transmission by up to 85%. That's a huge amount of wasted energy that's now saved, which can be used to actually power the chip.
And what that all boils down to is a near doubling of what we call power density. With a technology like PVAR, you can deliver way more power into the exact same amount of space. And that's what enables the next generation of these incredibly powerful and frankly incredibly power-hungry processors.
So, let's put all the pieces together. What does this all really mean? Well, it means we're clearly stepping into a brand new era of chip design. It's an era that's not going to be defined by just making things smaller, but by incredibly clever and creative engineering.
You see, the slowdown of Moore's Law, it wasn't the end of the road. It was actually a new beginning. The whole focus of innovation has shifted to customization. And we've just walked through 3 of the key technologies making it happen. Building up with chiplets, making memory smarter with custom SRAM, and delivering power more efficiently with PVR.
And it's so important to remember this isn't just some abstract thing for engineers in a lab. No way. This is the fundamental tech that's going to power the next huge leap forward in artificial intelligence, in cloud computing, and in all the services we're starting to rely on every single day.
So this new era of custom chip design is unlocking levels of performance that, honestly, we used to think were impossible. And that leaves us with one really exciting question to chew on. With this new power, what impossible problems are we going to solve next?